Ever wondered what truly drives the vehicles we rely on daily? From the quiet hum of your car engine to the thunderous roar of a jet taking flight.
Hmm,
It's all rooted in the fascinating, often hidden world of gas power cycles.
absolutely.
Today, we're embarking on a deep dive into the core principles behind these incredible machines, pulling insights from extensive research and engineering wisdom.
Yeah, and our mission isn't just to tell you how they work, right?
Exactly. We want to unpack the surprising engineering trade-offs, the clever innovations, and the fundamental limits that shape everything from an engine's design to the efficiency of your daily commute.
We're exploring the unseen forces that move our world.
So let's dive in.
What's truly fascinating here is witnessing how abstract thermodynamic cycles, these theoretical blueprints, really translate into the powerful, tangible engines we depend on.
Like seeing the theory become reality.
Precisely. We're going to peel back the layers, looking at the ideal models engineers use as their starting point, and then reveal how real-world limitations and, well, ingenious solutions bring them to life.
So you'll gain a whole new appreciation, hopefully, for the delicate balance of physics and practicality that defines our modern energy landscape. Okay, so to begin, what exactly defines a power cycle in an engineering context? And how do engineers classify these systems to even start making sense of them?
Okay. At its heart, a power cycle is simply a system designed to convert thermal energy into useful work, producing a net power output. Think of it as an engine, basically.
Right.
And engineers classify them to understand their fundamental operation. So first, we differentiate between power cycles, which generate work, and refrigeration cycles, which absorb heat to create a cooling effect.
And we're focused on power today.
Exactly. Our focus today is power. Then there's the working fluid. Gas cycles keep the fluid as a gas throughout, like air, whereas vapor cycles involve phase changes, like water turning to steam.
Got it. Gas cycles for us.
Gas cycles today, yeah. We also distinguish between closed cycles, where the fluid recirculates, and open cycles, where the fluid is continuously replaced, like a car engine exhausting combustion gases.
Makes sense.
And finally, internal combustion means fuel burns inside the working fluid, like in your car, while external combustion means it burns outside the system, as in a classic steam power plant.
So these classifications immediately tell an engineer about the fundamental constraints and maybe opportunities for a given design.
That's right. They set the stage for everything else.
And when engineers study these, they often talk about ideal cycles. But aren't real engines far more complex and, well, messy?
Absolutely. Oh, yes. Real-world cycles are inherently messy. They're plagued by friction, heat losses, non-equilibrium conditions, all sorts of things.
So why use the ideal models?
Well, that's why engineers lean so heavily on ideal cycles as their theoretical sort of North Star. These are simplified models where we assume perfect conditions. No friction, processes happening infinitely slowly, so everything's always in balance.
Okay, perfect insulation, negligible changes in kinetic or potential energies, that kind of stuff.
Exactly. While the numbers from an ideal cycle won't precisely match a real engine, they preserve the general characteristics.
Ah, so the trends are the same.
Precisely. This means if an ideal cycle predicts efficiency increases with, say, compression ratio,
Yeah.
a real engine will follow that same trend. It tells you which levers to pull in design.
Right. And speaking of performance, what's the ultimate theoretical limit? The ceiling for efficiency that any heat engine can achieve.
Yeah. That's where the concept of thermal efficiency comes in. It's simply the ratio of the network you get out to the total heat you put in.
Workout overheat in.
And the absolute theoretical best is the Carnot cycle. It represents the maximum possible efficiency for any engine operating between a given high-temperature heat source, TH, and a low-temperature heat sink, TL.
And there's a formula for that, isn't there?
There is.
Right.
Carnot equals 1 TLTH. And this formula reveals a fundamental truth. To maximize efficiency, you need to either supply heat at the highest possible average temperature or reject it at the lowest possible average temperature.
So it's all about that temperature difference.
It's critical. This is why material science, advanced cooling, heat management, they're just as critical as the cycle design itself. The laws of physics are holding us to these temperature limits.
Yet I always hear the Carnot cycle is notoriously impractical to actually build. Why is that?
Precisely. Yeah, while it's a theoretical marvel, the Carnot cycle demands perfectly reversible isothermal heat transfer,
Which means...
which would require impossibly large heat exchangers and, well, infinite time to operate. It's a physicist's dream, maybe, but not an engineer's practical blueprint.
Okay, so that's why you need other ideal cycles, right? Ones that are more realistic models for actual devices, even if they can't quite hit Carnot's peak.
Exactly. They provide a more achievable target.
And for visualizing all this, those PV and TS diagrams seem pretty fundamental. I remember those from physics.
They're indispensable tools. On both a PV, pressure volume diagram, and a TS, temperature entropy diagram, the area enclosed by the cycle's process curves represents the network produced.
Okay, the enclosed area is work.
Yep. And due to the first law of thermodynamics, that's also equal to the net heat transfer. The TS diagram is particularly insightful because the area under any process curve represents the heat transfer during that process. So any modification that increases the ratio of the enclosed work area to the heat addition area visually demonstrates an efficiency boost. It's a powerful visualization tool.
Okay, so given the complexity of actual engines, how do engineers simplify the working fluid in the combustion process for analysis without losing too much accuracy?
Right. They use a set of really powerful simplifications known as air standard assumptions. These allow for a much cleaner analysis mathematically.
What are they, generally?
Well, first, they assume the working fluid is just air, behaving as an ideal gas, and it continuously recirculates in a closed loop, even if a real engine is open.
Okay, so simplifying the fluid.
Second, all processes within the cycle are treated as internally reversible, meaning no internal friction or uncontrolled expansions. Smooth sailing, theoretically.
Yeah.
Third, the messy, complex combustion process is replaced by a simple, clean heat addition process from an external source, much easier to model.
Just add heat, basically.
And fourth, the exhaust process is replaced by a heat rejection process that simply brings the air back to its initial state, completes the loop.
Okay, and sometimes they simplify even further.
Yes, if they want to simplify even more, they use cold air standard assumptions. That adds the assumption that air has constant specific heats, typically evaluated at room temperature.
So even simpler math.
Right. These models, despite their simplicity, are incredibly useful for studying the qualitative influence of major design parameters. They let engineers quickly grasp fundamental relationships before diving into complex computer simulations.
Makes sense. Let's turn to something everyone's familiar with, the engines in our cars. What are the crucial parameters engineers focus on in these reciprocating piston cylinder engines?
Okay, good question. For these engines, like the ones in cars, trucks, generators, a key parameter is the compression ratio.
Right, I've heard that term.
It's simply the ratio of the maximum cylinder volume when the piston is at the bottom of its stroke to the minimum volume when it's at the top. Vmax over Vmin.
And it's a volume ratio, not pressure.
Correct. It's a volume ratio, and it's a fundamental lever engineers pull to dictate how much useful work you can squeeze out of a given amount of fuel.
Okay, compression ratio. What else?
Another vital metric is mean effective pressure, or MEP. Imagine if, throughout the entire power stroke, you had a constant pressure pushing the piston.
Like an average pressure.
Kind of, yeah. A fictitious constant pressure that would generate the exact same network as the actual complex varying pressure cycle. That's the MEP.
And higher is better.
A higher MEP means more network per cycle for a given engine size, indicating better engine performance, more bang for your buck, so to speak.
Okay. And how are these engines primarily categorized based on how they ignite the fuel?
Right. They're broadly classified by how combustion is initiated. You've got spark ignition SI engines, like your typical gasoline engine.
Yeah.
They use a spark plug to ignite the air-fuel mixture.
The standard car engine for most people.
Yeah. Then there are compression ignition, CI engines, famously known as diesel engines. Here, only air is compressed to such a high temperature that when fuel is injected, it ignites spontaneously on contact. No spark plug needed.
Heat does the work.
The heat of compression, exactly.
So let's dive into the Otto cycle. That's the ideal model for most gasoline engines, right? What are the key stages in this cycle?
That's right. The Otto cycle, named after Nicholas Otto, is the ideal representation of those spark ignition engines. Most common are four-stroke engines, where the piston completes 4 distinct strokes, 2 up, 2 down for each complete thermodynamic cycle.
And that takes 2 crankshaft revolutions.
2 revolutions, correct. These actual strokes are intake, compression, power or expansion, and exhaust. That's the mechanical reality.
But the ideal cycle simplifies this.
Yes. In the ideal Otto cycle, we model this with 4 internally reversible processes. First, isentropic compression, where the air is compressed without heat transfer, no losses. Then, constant volume heat addition. Yeah. This simplifies the rapid combustion process into an instant pressure rise at fixed volume.
The bang.
The idealized bang, yes. Third, isentropic expansion. That's your power stroke, where the hot gas pushes the piston down. Again, perfectly, no losses.
Work out?
And finally, constant volume heat rejection, which models the exhaust blowdown and cooling back to the initial state, again, instantly at fixed volume.
So 4 ideal steps replacing the messy reality.
Exactly. It gives us a framework.
And what about two-stroke engines? They seem less common in cars now, but you still see them in, like, chainsaws and stuff.
Right. Two-stroke engines cleverly pack all 4 functions: intake, compression, power, exhaust into just 2 piston strokes. That means a power stroke occurs every single revolution of the crankshaft.
Ah, twice as often as a 4-stroke.
Exactly. This makes them simpler, lighter, and cheaper, offering very high power-to-weight and power-to-volume ratios. Perfect for things like motorcycles, chainsaws, lawnmowers, portable stuff.
But they had downsides, right?
Yeah.
Efficiency, emissions.
Historically, yes. They were generally less efficient and dirtier due to incomplete exhaust scavenging. Some exhaust gas got left behind, and also some fresh fuel-air mixture escaping out the exhaust port before combustion.
Not ideal.
Not ideal, but modern advancements, things like direct fuel injection and stratified charge combustion, electronically controlled, are actually revitalizing them. They promise high performance and fuel economy with much cleaner emissions now, so they're making a bit of a comeback.
Interesting. Okay, so when we look at the ideal Otto cycle, what truly dictates its thermal efficiency? What are the main factors?
Under those cold air standard assumptions we talked about, the ideal Otto cycle's efficiency is fundamentally driven by just 2 parameters: the compression ratio and the specific heat ratio of the working fluid, usually air.
So higher compression ratio is better.
Yes. The more you compress the air before ignition, the higher the temperature and pressure before expansion, and the more work you can extract during that expansion stroke. So higher compression ratio means higher theoretical efficiency.
There's always a but, isn't there?
Ah, yes. Here's where it gets really interesting for engineers. If you push the compression ratio too high in a gasoline engine, you run into autoignition, or engine knock.
That pinging sound.
That's the one. The fuel-air mixture ignites prematurely and unevenly, creating damaging pressure waves and actually reducing performance. It's the inherent limit for gasoline engines.
So how did they deal with that historically?
Well, for decades, engineers added tetraethyl lead to gasoline. This increased the fuel's octane rating, essentially, its resistance to knock, which allowed them to design engines with higher, more efficient compression ratios.
But lead is bad, obviously.
Very bad for health and the environment. So it was phased out starting in the mid-70s. Now we rely on advanced fuel blends, better combustion chamber design, and sophisticated technologies like variable compression ratios and advanced ignition timing to walk that tightrope between high compression and avoiding knock.
And the other factor, the specific heat ratio, K.
Right. K also plays a role. Higher K values lead to higher theoretical efficiencies. Monatomic gases like argon or helium have the highest K, around 1.667.
But we use air.
We use air, which is mostly diatomic nitrogen and oxygen, with a K around 1.4. And the actual combustion products like CO2 and water vapor have even lower K values. So that's another factor pulling real-world efficiency down from the ideal.
So putting it all together, what kind of efficiencies do real gasoline engines typically achieve then?
In practice, actual spark ignition engines usually fall somewhere between 25% and 35% thermal efficiency, though continuous improvements in design, materials, and control systems means some new generation engines can push past 40%.
Still a big gap from the ideal cycle.
Oh, yeah.
Yeah.
The difference between ideal and actual efficiency really highlights the constant battle engineers fight against: friction, heat loss, incomplete combustion, and all those real-world imperfections.
And you mentioned earlier that 2-stroke engines can generate more power than a 4-stroke for the same size and RPM. How does that work, especially if they're often less efficient?
Ah, that's a great observation about the power output. It comes back to firing frequency. While a 4-stroke engine produces a certain amount of work per thermodynamic cycle, remember, it requires 2 full crankshaft revolutions to complete that cycle.
1 power stroke every 2 turns.
Right. A 2-stroke engine, on the other hand, completes its cycle and delivers a power stroke in just 1 revolution.
So it fires twice as often for the same RPM.
Exactly. So Even if the work per cycle is the same, a two-stroke engine can theoretically deliver double the power output at the same engine speed. It's a trade-off. More power density, historically at the cost of lower fuel efficiency and higher emissions, though that's changing now.
Okay, let's shift our focus to diesel engines.
Yeah.
What's a fundamental operating distinction compared to gasoline engines again?
Right. The diesel cycle, conceived by Rudolf Diesel, is the ideal model for those compression-ignition engines. The critical difference, the real game changer, is how combustion is initiated.
No spark plug.
No spark plug. In a diesel engine, only air is drawn in and compressed. It's compressed so much that its temperature rises incredibly high, well above the fuel's auto-ignition point.
So the air gets super hot just from squeezing it?
Super hot. Then, at the right moment, diesel fuel is injected into this extremely hot air, and it ignites instantly on contact, spontaneously.
Okay, and what are the main engineering advantages of doing it that way?
The biggest advantage is this. Because you're only compressing air, there's no fuel-air mixture present during the compression stroke that could auto-ignite prematurely. There's essentially no risk of engine knock.
Ah, so that limitation from gasoline engines is gone.
It's gone. This freedom allows diesel engines to operate at much higher compression ratios, typically between 12 and 24, compared to maybe 8 to 12 for gasoline engines.
And higher compression means?
Higher efficiency. That significantly boosts their potential thermal efficiency compared to gasoline engines. Plus, another practical advantage is they can often use less refined and thus sometimes less expensive fuels.
Okay, so how does the ideal diesel cycle's sequence of processes differ from the Otto cycle then? Is it just the ignition?
The processes are quite similar, but there's one crucial difference in the heat addition phase, which reflects that injection and burning process.
What is it?
The ideal diesel cycle consists of, first, isentropic compression, just like Otto, but then it's followed by constant pressure heat addition.
Constant pressure, not constant volume like Otto.
Correct. This models the fuel being injected and burning steadily as the piston starts moving down slightly, maintaining pressure, rather than the Otto's instant explosion at fixed volume.
Okay, that makes sense.
Then comes isentropic expansion, the power stroke like Otto, and finally, constant volume heat rejection like Otto to get back to the start.
So the key difference is constant pressure heat addition versus constant volume. What does that mean for efficiency? Is a diesel engine always more efficient than a gasoline engine?
This is where context is really key. It's a common misconception. If you compare an ideal Otto and an ideal diesel cycle operating at the exact same compression ratio, the Otto cycle is actually theoretically more efficient.
Really? Why?
Because adding heat at constant volume, Otto, happens at a higher average temperature than adding it at constant pressure, diesel, for the same starting point after compression. And remember, higher average temperature of heat addition boosts efficiency.
Okay, but you said diesels are generally more efficient.
Exactly, because that comparison is purely theoretical. In the real world, diesel engines operate at much higher compression ratios than gasoline engines can tolerate. That ability to use high compression ratios, thanks to their ignition method, is what makes them generally more efficient in practice. Their design freedom gives them the real-world edge.
Got it. So where do we typically see these highly efficient diesel engines making the biggest impact?
Their superior efficiency, durability, and high torque make them indispensable for heavy-duty applications requiring substantial, sustained power. Think locomotives, large ships, heavy trucks, buses, agricultural machinery, and emergency power generation units.
Big stuff.
Big stuff, mostly. Consider the sheer scale. There was a 12-cylinder Fiat Marine diesel engine built back in 1964 that produced an astonishing 25,200 horsepower at just 122 revolutions per minute.
Wow.
Modern automotive diesels typically achieve thermal efficiencies in the 35% to 40% range, which is very good. And some massive low-speed marine diesels used in container ships can exceed 50% thermal efficiency, incredibly efficient machines.
And you mentioned another cycle, the dual cycle.
Yeah, it's worth noting that for modern high-speed diesel engines, the ideal diesel cycle with its pure constant pressure heat addition isn't always the best fit. Combustion happens very fast. So the dual cycle is often a more realistic representation.
How does that work?
It models the combustion process as a combination of both constant volume heat addition, like Otto, and constant pressure heat addition, like diesel. It's a hybrid, really, and in fact, you can see both the Otto and diesel cycles as special limiting cases of this more general dual cycle.
Interesting. Okay, we've talked about Otto and diesel, which are workhorses but have limitations, and Carnot, which is theoretically perfect but impractical. Are there any other cycles that promise Carnot-level efficiency but might be slightly more buildable?
Yes, that's a great question. There are two other important theoretical cycles, the Stirling cycle and the Ericsson cycle. These are also totally reversible cycles, meaning, in theory, they can achieve the same maximum thermal efficiency as the Carnot cycle when operating between the same high and low temperature limits.
Okay, Stirling and Ericsson. How do they manage to reach that totally reversible status if they don't follow Carnot's exact steps? What's different?
They achieve this perfect reversibility, theoretically, through a clever mechanism called regeneration. Like Carnot, they have two isothermal processes for heat addition at TH and heat rejection at TL. But instead of Carnot's two isentropic adiabatic processes, they use two regenerative processes.
Regenerative process.
Yes. For the Stirling cycle, these are constant volume regeneration processes. For the Ericsson cycle, they are constant pressure regeneration processes.
Okay, but what exactly is this regeneration that makes them so potentially efficient? What's it doing?
Regeneration involves a special device, logically called a regenerator. Think of it as a thermal sponge or a temporary heat storage unit within the engine.
A thermal sponge.
Okay, so during one part of the cycle, the hot working fluid passes through this regenerator and deposits some of its heat into the regenerator material. Then, later in the cycle, when the working fluid is cooler, it passes back through the same regenerator and picks up or regenerates that stored heat.
Ah, so it's preheating itself using its own waste heat.
Exactly. It's like the engine is efficiently borrowing thermal energy from one part of its cycle and paying it back in another part. This significantly reduces the amount of external heat you need to add from fuel and the amount of waste heat you need to reject, boosting the cycle's overall efficiency dramatically.
They sound incredibly promising on paper. High efficiency, potentially reversible. Why aren't we seeing Stirling or Ericsson engines everywhere then?
Well, while they are conceptually elegant and theoretically super efficient, they still present significant practical challenges for engineers trying to build them.
Like what?
Achieving truly reversible heat transfer, even with regeneration, demands enormous heat exchanger surface areas or requires the engine to run very, very slowly. Real regenerators aren't 100% effective. They don't capture and return all the heat perfectly, and they also introduce pressure losses as the fluid flows through them.
So practical hurdles.
Big practical hurdles. However, there's definitely renewed interest in them, especially Stirling engines, because of their high potential efficiency, their ability to run on almost any external heat source, since they are external combustion engines, and their potential for quieter operation and cleaner emissions.
External combustion. So the fuel burns outside the cylinder.
Exactly. That's a key advantage. You burn the fuel outside, heating the working fluid through a heat exchanger. This allows for a more complete combustion, reducing pollutants. It also means you can use a wide variety of fuels, solar energy, biomass, waste heat, whatever. And because they typically operate on a closed cycle, you can use ideal working fluids like hydrogen or helium, which have very desirable thermodynamic properties, instead of just air.
So despite the challenges, the core idea is powerful.
Immensely powerful. The strong message these cycles convey to design engineers is that regeneration is a game changer for efficiency. And it's absolutely no coincidence that modern gas turbine power plants, which we'll get to, extensively incorporate regeneration to boost their performance.
Okay, good segue. Let's move to another major power generator, gas turbines. They're the heart of modern aircraft and many ground-based power plants. What's the fundamental cycle behind them?
Right. The Brayton cycle is the ideal cycle for modern gas turbine engines. It was first proposed by George Brayton way back around 1870. The key difference from the reciprocating engines we've discussed is that both the compression and expansion processes occur in rotating machinery. A compressor and a turbine, not pistons in cylinders.
Continuous flow, then.
Continuous flow, exactly. Gas turbines typically operate on an open cycle. Fresh air is drawn in, compressed by a rotary compressor. Then it's mixed with fuel and burned continuously at constant pressure in a combustion chamber. These hot, high-pressure gases then expand through a turbine, making it spin and produce power. Finally, the exhaust gases are discharged to the atmosphere.
Okay, and the ideal model for this, using those air standard assumptions again, how does that look?
Using the air standard assumptions, the ideal Brayton cycle is modeled as a closed cycle with 4 internally reversible processes. It starts with isentropic compression in the compressor.
Raising the pressure.
Raising the pressure, right. Then constant pressure heat addition, which replaces the continuous combustion process.
Adding energy at high pressure.
Correct. Next is isentropic expansion through the turbine, where the energy is extracted to produce work.
The power generation step.
And finally, constant pressure heat rejection, where the cycle theoretically rejects waste heat to return the air to its initial state, closing the loop.
Okay, similar steps to diesel in terms of pressure changes, but continuous flow. How does its thermal efficiency scale, and what typically limits it in the real world?
The thermal efficiency of the ideal Brayton cycle depends primarily on the pressure ratio. That's the ratio of the maximum pressure after compression to the minimum pressure before compression, and also on the specific heat ratio K of the air.
And efficiency increases with pressure ratio.
Yes, efficiency increases significantly with both pressure ratio and K. This means engineers are always striving to push that pressure ratio higher and higher to get more efficiency.
So what stops them from just using incredibly high pressure ratios?
The major practical limitation is the maximum temperature the turbine blades can withstand at the turbine inlet right after combustion. This temperature, often called the firing temperature, is fiercely guarded by material science. We need advanced superalloys, ceramic coatings, sophisticated internal cooling passages.
Because if those blades fail,
Catastrophic failure, the engine destroys itself. So engineers have to find a delicate compromise between pushing for the highest possible firing temperature, and thus pressure ratio for efficiency, and ensuring the engine's reliability and lifespan. There's also an optimal pressure ratio for maximum network output, which might be different from the one for maximum efficiency.
and you mentioned something about gas turbines having a high backwork ratio. What's that?
Ah, yes, that's a really significant characteristic. The backwork ratio is the ratio of the work consumed by the compressor to the total work produced by the turbine.
So how much of the turbine's power goes just to run the compressor?
Exactly. And in gas turbines, this ratio is surprisingly high, often 40% to 80%. More than half of the turbine's output can be used just to drive the compressor needed to feed it high-pressure air.
Wow, that seems like a lot.
It is. This contrasts sharply with, say, steam power plants based on the Rankine cycle. There, the work needed to pump the liquid water back to high pressure is only a tiny fraction, maybe 1–2% of the turbine output. This high backwork ratio makes gas turbine efficiency very sensitive to losses in the compressor and turbine.
So given that high backwork ratio and the temperature limits, how have gas turbines become so incredibly powerful and efficient today? What were the breakthroughs?
Gas turbine development since the 1930s has been a story of relentless innovation, really focusing on three main areas. First, as we touched on, increasing turbine inlet temperatures. We've gone from around 540 degrees C or 1,000 degrees AF in the 1940s to over 1,425 degrees or 2,600 degrees AF today in advanced machines. That's purely down to breakthroughs in material science and those ingenious cooling techniques.
Okay, hotter is better, within limits. What else?
The second area is increasing the efficiencies of the turbomachinery itself, the compressors and turbines. Advances in aerodynamics, computational fluid dynamics, CFD, and precision manufacturing have drastically reduced aerodynamic losses and improved how effectively they compress air and extract energy. Small percentage point gains here make a big difference because of that backwork ratio.
Better blades, better flow.
Better everything. And third, adding sophisticated modifications to the basic Brayton cycle. This is where things like intercooling, reheating, and regeneration come in techniques designed specifically to tackle the high backwork ratio and improve overall performance.
And the results are impressive.
Absolutely. For example, a common aeroderivative gas turbine like the General Electric LM2500, used in naval ships and industrial applications, has the simple cycle thermal efficiency around 37%. But large, advanced, simple cycle power plants designed just for electricity generation now achieve up to 44% efficiency, with single units producing over 500 megawatts of power. That's huge.
It's also striking how sensitive these systems must be to real-world imperfections compared to the ideal cycle.
Precisely. You hit the nail on the head. Actual gas turbine cycles deviate significantly from the ideal Brayton cycle because of unavoidable things like pressure drops in the combustion chamber and ducting, and especially irreversibilities, friction, and turbulence in the compressor and turbine.
So how do engineers account for that?
To account for this in design and analysis, engineers use isentropic efficiencies for each component. There's a compressor isentropic efficiency and a turbine isentropic efficiency. These basically measure how close the actual component comes to performing its ideal, frictionless isentropic process.
And these efficiencies are less than 100%.
Always less than 100% in reality, maybe 80–90% for good components. But the impact is significant. For instance, remember that ideal Brayton cycle example with 42.5% thermal efficiency? If you add realistic component efficiency, say 80% for the compressor and 85% for the turbine, the overall actual cycle efficiency can plummet down to maybe 26.6%.
Wow, that's a huge drop.
It is. The stark difference really underscores why every single percentage point of improvement in compressor and turbine aerodynamic efficiency has been so incredibly critical to the success of the modern gas turbine.
So how do engineers push the boundaries even further with Brayton cycles, especially trying to mitigate that high back work ratio? You mentioned modifications.
Right. The net work output of a gas turbine, remember, is simply the turbine work minus the compressor work. 1 net equals WT/WC. So engineers realized they could increase this network in two main ways, either by decreasing the compressor work, WC required, or by increasing the turbine work, WT produced, or ideally doing both.
Okay, how do you decrease the compressor work?
You use intercooling. Instead of compressing the air all at once, you compress it in stages. Between the stages, you pass the partially compressed hot air through a heat exchanger and intercooler to cool it down before it enters the next compression stage.
Why does cooling it help?
Because compressing cooler, denser air takes less work. By using multiple stages with intercooling, you significantly reduce the total work required by the compressor, making the overall compression process approach an ideal, energy-saving, isothermal, constant temperature path.
Clever. And how do you increase the turbine work?
You use reheating. Similar idea, but on the expansion side. Instead of expanding the hot gas through the turbine all at once, you do it in stages. Between the turbine stages, you reheat the partially expanded gas by burning more fuel in it.
Adding more heat mid-expansion.
Exactly. Since the gas leaving the first turbine stage is still very hot and usually has plenty of excess oxygen, because gas turbines run very lean, you can simply inject and burn more fuel right there before it enters the next turbine stage. This increases the temperature and energy available for the subsequent expansion, boosting the total work output from the turbine. Like intercooling, multi-stage expansion with reheating helps the overall expansion process approach an ideal work-maximizing isothermal path.
Okay, intercooling reduces compressor work, reheating boosts turbine work. Sounds like a win-win for net power. But you hinted earlier that just doing these doesn't necessarily improve the thermal efficiency. Why not?
You're right to catch that subtlety. It seems counterintuitive, but while intercooling and reheating definitely increase the network output and improve the back work ratio, less turbine work is consumed by the compressor, they can actually decrease the overall thermal efficiency if used alone.
How come?
It comes back to those average temperatures. Intercooling, by cooling the air mid-compression, lowers the average temperature at which heat is added in the main combustion chamber. And reheating, by adding heat mid-expansion, increases the temperature of the gas leaving the final turbine stage, thus increasing the average temperature at which heat is ultimately rejected by the cycle. Both of these effects tend to hurt thermal efficiency according to Carnot's principles.
Ah, okay. So they boost power, but potentially at the cost of fuel economy if you're not careful.
Exactly. That's why, for optimal performance, especially in stationary power generation where fuel cost is critical, intercooling and reheating are almost always used in conjunction with regeneration.
Okay, so let's bring regeneration back into the picture for Brayton cycles. How does it integrate here?
Right. The beauty of regeneration in a Brayton cycle lies in utilizing the heat from the turbine exhaust. Even after expansion, the exhaust gas leaving the turbine is often still very hot, frequently much hotter than the air leaving the compressor before combustion.
So there's useful energy being wasted there.
A lot of useful energy. A regenerator, also sometimes called a recuperator in this context, is a clever counterflow heat exchanger. It takes those hot exhaust gases coming out of the turbine and uses them to preheat the relatively cooler, high-pressure air coming out of the compressor before that air enters the combustion chamber.
So it's using waste heat to reduce the fuel needed.
Precisely. It directly increases the thermal efficiency because less external fuel needs to be burned in the combustor to reach the desired turbine inlet temperature. You're recycling waste heat internally.
And how well does a regenerator work?
Its performance is measured by its effectiveness, which is basically the ratio of the heat it actually transfers to the maximum possible heat it could transfer given the temperature difference. Higher effectiveness means more heat recovered and more fuel saved.
What's the downside?
The trade-off is that a highly effective regenerator needs to be physically larger, heavier, and more expensive. It can also cause a pressure drop in both the air and exhaust streams, which slightly hurts performance. Regeneration tends to be most effective financially and thermodynamically at lower pressure ratios where the temperature difference between the turbine exhaust and compressor outlet is largest.
Okay, so what happens when you combine all three modifications, intercooling, reheating, and regeneration? Is that the ultimate Brayton cycle?
That's where the true thermodynamic magic happens for gas turbines. When you effectively combine multi-stage compression with intercooling, multi-stage expansion with reheating, and efficient regeneration, you start pushing the cycle towards its maximum potential.
How so?
The more stages of compression and expansion you add, combined with ideal intercooling, reheating, and regeneration, the closer the overall cycle's processes approach isothermal heat addition and rejection. And what ideal cycle features isothermal heat addition and rejection with regeneration?
The Ericsson cycle.
The Ericsson cycle, exactly. So this complex, modified Brayton cycle starts to emulate the highly efficient totally reversible Ericsson cycle, and thus it approaches the theoretical Carnot efficiency limit for the given operating temperatures.
Can you give an example of the improvement?
Sure. Remember that ideal simple Brayton cycle with 42.5% efficiency. If you modify it ideally with just 2 stages of compression and expansion, incorporating perfect intercooling, reheating, and regeneration, the theoretical thermal efficiency can jump to a stunning 69.6%.
Wow, that's a massive increase.
Yeah.
From 42% to nearly 70%.
A massive 63% increase in that ideal case. Now, adding more and more stages eventually brings diminishing returns and the complexity and cost increase rapidly. But incorporating just 1 or 2 stages of these modifications, especially regeneration, can dramatically boost efficiency, making them economically justifiable and a cornerstone of modern high-performance combined cycle gas turbine power plants, which achieve over 60% real-world efficiency.
It's amazing. Okay, shifting gears now, but staying with gas turbines. How do these principles apply to the powerful jet engines that literally propel aircraft around the world?
Right. Aircraft are propelled by jet propulsion cycles, which are essentially modified open-cycle gas turbine engines based on the Brayton cycle. The crucial difference, the design philosophy change compared to a stationary power plant, is the purpose of the turbine.
How so?
In a pure turbojet engine, the turbine is designed to generate just enough power to drive the compressor and maybe some auxiliary equipment, like generators and hydraulic pumps. The network output from the shaft is deliberately designed to be zero, or very close to it.
So the turbine isn't driving a generator or propeller directly?
Not in a basic turbojet, no. Instead, the goal is to leave the high-temperature, high-pressure gases exiting the turbine with as much energy as possible. These gases are then accelerated to a very high velocity as they expand through a specially shaped nozzle at the back of the engine.
And that high-speed exhaust provides
The thrust. According to Newton's third law, expelling that massive gas backwards at high speed creates an equal and opposite force pushing the engine, and thus the aircraft, forwards.
So if there's no net shaft work output, how is a jet engine's performance measured or defined? We can't use the same thermal efficiency, can we?
You're right. The standard thermal efficiency, network out, heat in, doesn't make sense here because the network is 0. Instead, we talk about thrust, F, which is calculated from the change in momentum of the air passing through the engine. F equals mF vexit vinlet, where m dot is the mass flow rate of air, vexit is the exhaust velocity, and vinlet is the aircraft's inlet air velocity.
Okay, thrust is the force. What about efficiency?
For efficiency, we use 2 main concepts. First is propulsive power, W do OTP, which is the useful power delivered to the aircraft. It's simply the thrust multiplied by the aircraft's velocity, W do OTP equals F of aircraft. This is the rate at which the engine is doing work on the aircraft.
Makes sense. Thrust times speed.
Then we define the propulsive efficiency. This is the ratio of that useful propulsive power to the rate at which energy is released by burning fuel, often approximated as the rate of heat addition, Q Dalton. So, EPP equals W dot TP Q Dalton. It tells us how effectively the engine converts the thermal energy from the fuel into useful aircraft motion.
Where does the rest of the fuel energy go?
The energy from the fuel that doesn't become propulsive power ends up primarily as the kinetic energy of the exhaust gases leaving the nozzle relative to the ground, and as an increase in the enthalpy, residual heat, of those exhaust gases. For the highest possible propulsive efficiency, ideally, you want the exhaust gases to leave the nozzle at the same velocity as the aircraft itself. Vexit equals venlet. That way, their velocity relative to the ground is 0 and no kinetic energy is wasted in the exhaust wake.
Interesting. So you want high thrust, but ideally by moving a large mass of air relatively slowly, rather than a small mass very fast.
Exactly. That's the key insight that led to the next generation of jet engines.
So what are some of the ingenious modifications engineers developed to push the boundaries of jet engine design beyond the basic turbojet?
Well, the initial breakthrough was the pure turbojet engine developed around World War II and powering the first commercial jets in the 1950s. But engineers quickly realized that the turbojet, while great for high speeds, was noisy and relatively inefficient at lower speeds because its Vexit was so high. They needed a way to get closer to that ideal of Vexit-matching Vinlet.
So they looked for ways to move more air.
Precisely. This led to the turbofan, or fanjet engine, which is now the dominant type powering virtually all commercial airliners. In a turbofan, the core engine, compressor, combustor, turbine, is still there, but the turbine drives a much larger fan at the very front.
Like a ducted propeller.
Kind of, yes. This large fan forces a significant amount of air around the core engine through a bypass duct. This bypassed air isn't involved in combustion, but it gets accelerated by the fan and mixes with the hot core exhaust, producing much of the thrust.
And this helps efficiency.
Greatly. By moving a larger total mass of air, core plus bypass, at a lower average exit velocity, turbofans generate thrust much more efficiently and are significantly quieter than pure turbojets, especially at takeoff and landing speeds. They're defined by their bypass ratio, the ratio of the mass flow rate of bypassed air to the mass flow rate through the core engine. Modern high bypass turbofans can have bypass ratios of 5.1, 10.1, or even higher. They were absolutely key to the success of jumbo jets and affordable air travel.
Okay, turbofans are dominant. What else is out there?
Well, if you take the turbofan concept and essentially remove the fan cowl entirely, you get prop jet or turboprop engines. Here, the gas turbine's primary job is to drive a large conventional propeller through a gearbox.
Like on smaller commuter planes.
Exactly. Propellers are generally more efficient than even turbofans at lower speeds and altitudes, say below Mach 0.6. Turboprops have extremely high effective bypass ratios, sometimes up to 100.1. There are also newer prop fan or unducted fan designs that try to combine the efficiency of propellers with the speed capabilities of turbofans using advanced, swept blade shapes.
What about military applications or high speed?
For military aircraft needing bursts of speed, afterburners are common. These are essentially fuel injectors placed in the exhaust pipe between the turbine and the nozzle. They spray extra fuel into the hot, oxygen-rich exhaust gas, creating a secondary combustion phase.
Like a second engine stage.
Sort of. It dramatically increases the exhaust temperature and velocity, providing a huge temporary boost in thrust, maybe 50% or more, but it burns fuel at an enormous rate, so it's only used for short periods, like takeoff or combat maneuvers.
And for really high speeds.
For very high speeds, Mach 2 and beyond, you have ramjets. These are ingeniously simple, basically just specially shaped tubes with no moving compressor or turbine parts. They rely purely on the ram effect of the incoming high-speed air being forced into the inlet and slowing down, which compresses it. Fuel is added and burned, and the hot gas accelerates out the nozzle. They need to be already moving fast to work at all. Scramjets, supersonic combustion ramjets, are similar but designed for even higher speeds, Mach 5 plus way, where combustion actually occurs while the airflow inside is still supersonic.
Oh. And finally, rockets.
And rockets, of course, are different again. They are entirely self-contained propulsion systems carrying both their own fuel and their own oxidizer. This means they don't need atmospheric air to operate and can work in space. They generate thrust by expelling the combustion products at extremely high velocity through a nozzle.
A whole spectrum of jet propulsion technologies.
A fascinating spectrum, all stemming from those basic Brayton cycle principles.
Okay, let's take a step back. Beyond just tracking energy in and out with thermal efficiency, the second law of thermodynamics tells us about the quality of energy and where its potential is irreversibly lost. How does this concept of exergy apply to the efficiency of these power cycles we've discussed?
This is a profoundly important point. Moving beyond just the first law, energy conservation, to the second law, entropy and irreversibility, while those ideal Carnot, Ericsson, and Stirling cycles are theoretically totally reversible and have zero internal or external irreversibilities, meaning zero exergy destruction.
Exergy being the measure of useful work potential.
Exactly, the maximum possible useful work you could get from a system or energy source relative to its environment. Those cycles ideally destroy no exergy. However, the ideal Otto, Diesel, and Brayton cycles, even in their ideal forms, are only internally reversible.
Meaning no friction inside,
but they still inherently suffer from external irreversibilities, primarily due to the heat transfer occurring across a finite temperature difference between the working fluid and the external heat source or sink. That heat transfer across a temperature gap always destroys exergy, always reduces the potential to do work.
So how does analyzing exergy destruction help engineers?
Exergy destruction, sometimes called irreversibility, helps us pinpoint where in the cycle the greatest inefficiencies, the biggest losses of work potential, truly lie. It's calculated as x dest equals T0, where T0 is the absolute temperature of the surroundings, and Sujin is the entropy generated by the irreversible process. By quantifying the exergy destroyed in each step of a cycle, engineers can see where the thermodynamic weak spots are.
Do you have an example?
Sure. What's often fascinating and maybe counterintuitive is that in an ideal Otto cycle, for instance, even though the isentropic compression and expansion steps are theoretically perfect, zero exergy destruction, analysis shows that the largest single portion of exergy destruction often occurs during the heat rejection process, process 4-1.
Even though it's modeled as ideal. Why?
Because that heat is being rejected from the relatively high temperature working fluid directly to the low temperature surroundings across a large temperature difference. That large ADO during heat transfer is a major source of irreversibility and lost work potential. This is crucial information for engineers. It tells them that even after extracting all the mechanical work you can, finding ways to reject the waste heat more efficiently, perhaps by using it for something else, like in cogeneration or combined cycles, is critical for truly optimizing the system's use of the fuel's potential.
So it's not just about maximizing the raw energy transformed into work, first law efficiency, but about minimizing the destruction of the potential for work, second law efficiency.
Exactly. That's precisely what second law efficiency, often denoted, captures. It's defined as the ratio of the useful work actually recovered, the network output, to the maximum possible useful work that could have been recovered from the heat input, which is the exergy supplied by the heat source.
So it compares actual work to the theoretical best work potential.
Precisely. It tells us how effectively the system converts the quality, not just the quantity, of the energy input into useful work. For example, that ideal Otto cycle might have a thermal first law efficiency of, say, 52.3%, but its second law efficiency might be calculated as 63%.
What does that difference tell us?
It tells us that while the engine is converting over half the heat energy into work, it's still only realizing 63% of the theoretical maximum work that was potentially available from that high temperature heat relative to the surroundings. The remaining 37% of the work potential is being irreversibly destroyed, mostly during that heat rejection process and the heat addition process, due to the temperature gap there too. Second law analysis provides a much deeper insight into thermodynamic perfection and where the biggest opportunities for improvement really lie.
That's a really useful perspective. Okay, so let's bring this all home. What does this deep dive into gas power cycles, from ideal theories to real-world engines and efficiency limits, mean for us, the everyday drivers? How do these complex thermodynamic principles translate into practical ways we can truly save fuel and money?
It's all about connecting the dots, understanding that fuel consumption isn't just about the engine's inherent design efficiency. It's heavily influenced by how we operate and maintain our vehicles. Essentially, how we interact with the engine's thermodynamic cycles day to day.
And it matters, right? Transportation fuel use is huge.
Absolutely huge. For perspective, something like 2/3 of all the oil used in the U.S. is for transportation, and roughly half of that amount is consumed just by passenger cars and light trucks. So even seemingly small changes in our individual driving habits and maintenance can have a massive compounding effect when millions of us do them.
Okay, so what can we do before even hitting the road? What are some pre-driving tips rooted in these principles?
Okay, quite a lot actually. First, think about the minimum octane rating recommended by your car's manufacturer. Using higher octane fuel than required doesn't magically make your car more powerful or efficient if it wasn't designed for it.
It just resists knock better.
Exactly. It just has higher resistance to engine knock, which is only needed if your engine operates at high enough compression ratios or under conditions prone to knock. If your engine doesn't need it, paying extra for premium is literally pouring money out of your tank for zero benefit.
Good tip. What else?
Avoid overfilling your gas tank. Don't top it off after the muzzle clicks off. That extra fuel can easily spill or evaporate, which not only wastes money, but surprisingly, each gallon lost this way emits as much polluting hydrocarbon vapor as driving 7,500 miles.
Wow, really?
Really? Also, if possible, park your car in a garage, especially in cold weather. A warmer engine at startup consumes less fuel during that initial warm-up period as it tries to reach its optimal operating temperature more quickly. Less fuel wasted just getting things up to temp.
Makes sense. And idling.
Definitely avoid extended idling. An idling engine is still burning fuel just to overcome internal friction and power accessories, but it's producing zero useful propulsive work. Modern engines warm up faster by being driven gently. If you anticipate being stopped for more than, say, 60 seconds, turning the engine off actually consumes less fuel than letting it idle for that time, plus less pollution and wear.
What about carrying extra weight?
Lighten your load. Every extra 100 pounds, about 45 kilograms you carry around, decreases your fuel economy by roughly 1 to 2% because the engine has to do more work to accelerate and maintain speed. So take unnecessary items out of your trunk or back seat. And roof racks. Even an empty one significantly increases aerodynamic drag, forcing your engine to work harder, especially at highway speeds. A loaded roof rack can increase highway fuel consumption by up to 5% or even more.
And tires. You mentioned those are crucial.
Oh, absolutely crucial, and probably the easiest win. Maintain proper tire inflation. Underinflated tires, even by just a few size, significantly increase rolling resistance. Think of it as driving on slightly squishy wheels. The engine has to constantly overcome that extra drag. Just being 2 psi underinflated can increase fuel consumption by 1%. Check your tire pressure monthly using the pressures listed on the sticker inside your driver's side door jamb, not the maximum pressure molded on the tire sidewall. It takes minutes and saves real money.
Okay, those are great pre-driving tips. What about while we're actually driving? How can our driving habits directly apply these efficiency principles?
Our driving habits themselves can make a huge difference, easily improving fuel economy by 10% or more, sometimes much more. The biggest one. Avoid quick starts and sudden stops. Be smooth.
Jackrabbit starts are bad.
Very bad for fuel economy. Aggressive acceleration demands sudden, large amounts of fuel injection and forces the engine to operate outside its most efficient zones. Flooring it also often causes unnecessary downshifts. Smooth, gradual acceleration and anticipating stops so you can brake gently conserve the engine's work, saves fuel, reduces wear on brakes and tires, and is generally safer.
What about speed? Faster isn't better.
Definitely not for fuel economy. Drive at moderate speeds. Remember how aerodynamic drag increases rapidly? It's a major force your engine has to overcome, especially at highway speeds. A typical car uses about 15% more fuel at 65 mph or 105 kilometers, and a whopping 25% more fuel at 70 mph, 113 kilometers, compared to cruising at 55 mph, 88 kilometers. The engine simply has to produce significantly more power and burn more fuel to push the air out of the way.
But going too slow isn't efficient either, right?
Correct. Efficiency also tends to drop off below about 30 mph, 50 kilometers, because the engine's internal friction and pumping losses become a larger percentage of the power being produced. There's usually a sweet spot, often between 45 and 60 mph, depending on the car.
So aim for smoothness and moderation. What else?
Maintain a constant speed whenever possible and safe. Using cruise control on the highway is a prime example of optimizing engine operation. Every time you unnecessarily speed up and slow down, you're wasting energy. Every hard press of the accelerator injects more fuel than needed.
Anticipation helps here too.
Huge help. Anticipate traffic flow. Look well ahead. By adjusting your speed early for upcoming traffic lights, slowing vehicles, or curves, you can often avoid unnecessary braking and subsequent reacceleration, which are major fuel wasters. Driving smoothly saves fuel up to 10% potentially just from this.
Gear selection matters too.
Yes. Use the highest appropriate gear, overdrive, without lugging the engine. Higher gears lower the engine's RPM revolutions per minute for given road speed. Lower RPM generally means fewer combustion cycles per minute and less internal friction, saving fuel and reducing engine wear during steady cruising. Let the automatic transmission do its job or shift up early in a manual.
And the age-old question, air conditioning versus open windows.
Yes. Use AC sparingly, as it definitely makes the engine work harder. The compressor needs power. Using AC can increase fuel consumption by 3–4% on the highway and potentially up to 10% in heavy stop-and-go city traffic where engine loads are lower. However, at highway speeds, say above 45–50 mph, driving with wide-open windows creates significant aerodynamic drag, which can actually waste more fuel than running the AC. So the general rule is, in town, try open windows first. On the highway, AC is usually more efficient than wide-open windows. Partially open windows are a compromise.
Good practical advice. And finally, after driving, what's important for maintaining that efficiency long-term?
Proper, consistent vehicle maintenance is absolutely paramount. It ensures all the systems related to the engine's operation are working as efficiently as designed.
Like what specifically?
Regular checks and changes of fluids, especially engine oil, belts and hoses, keeping those tires properly inflated as we hammered home, and crucially, replacing clogged filters, air filter, fuel filter, oil filter, according to the manufacturer's schedule. A severely clogged air filter, for example, can restrict airflow into the engine, forcing it to work harder and potentially increasing fuel consumption by up to 10% because it messes up the air-fuel ratio and reduces the engine's ability to breathe efficiently. Clean oil reduces internal friction, extends engine life, and ensures optimal performance. Regular tune-ups, check spark plugs, and ignition systems. All these things contribute directly to maximizing the work output for the fuel burned.
So bringing it all back to where we started our deep dive, what's the overarching message here from understanding gas power cycles?
It means that the relentless pursuit of efficiency isn't just something confined to engineers designing cutting-edge jet engines or massive power plants in a lab. It's truly a holistic, continuous process. It extends to every single aspect of our interaction with these power-producing devices, right down to the cars we drive every single day.
So knowledge empowers us.
Absolutely. From making informed choices when purchasing an energy-efficient vehicle in the first place, to adopting smart driving habits that minimize wasted energy, and committing to consistent maintenance that keeps the engine running optimally. Understanding these underlying principles of thermodynamics and gas power cycles truly empowers us. It allows us to make conscious decisions that not only save us fuel and money, but also collectively contribute to reducing emissions and fostering a healthier environment. It connects the complex science to our daily actions.
What an incredible journey that was.
Yes.
We've gone from the fundamental principles powering our modern world, delving into the elegant theory of ideal cycles, confronting the surprising nitty-gritty challenges like engine knock, and even landed on the often overlooked yet profound impact of something as simple as a properly inflated tire.
It really does underscore how deeply the laws of thermodynamics are interwoven with our daily lives, doesn't it? Influencing everything from the grand designs of global transportation networks down to the seemingly small, mundane choices we make in our own driveways and garages.
Absolutely. So for you, our curious listener, let's leave you with this final provocative thought to chew on. What other invisible thermodynamic battles are being fought constantly in the machines and systems all around you? Your refrigerator, your power grid, your own body even. And how might understanding those hidden energy transformations empower you to see the world, and perhaps your own impact on it, in an entirely new, more informed light?